The mighty surface current. Immense oceanic rivers of mass transport. Wind-driven water movement, responsible for transporting unimaginable tropical heat to the polar regions of Earth, making areas of the planet that would otherwise be inhabitable habitable. So, use your imagination, or you don't even have to. With our modern technology and incredible graphics, we can bring you out, away from Earth, just like you were in space, so you can see these phenomena right from the comfort of your own living room. Never before have we been able to bring this right to you. So why are we out here? Why are we showing you this? Well, in the surface of the ocean lies these incredible rivers, circulating the globe. Places like England and Scotland, which would otherwise be frozen tundra, are beautiful landscapes of lush greenery. In this way, the planet turns.
Even I think this is ridiculous.
These amazing capabilities. Surface currents, movement, wind, the atmosphere, all brought to you from right here where it all happens. All right, maybe while we're still talking about these global phenomena, we'll stick to inside where I can show you things like this. So this is just a satellite photo / composite computer-generated thing of all the surface currents around the planet. Okay, and you can see them moving around just like the thermohaline. These are global phenomena. However, we're going to see that some of their properties are a little bit smaller scale and actually happen a little bit faster. So we're going to take this and let's just slow it down, and we'll take a picture of the whole Earth. And these little blue lines here are just showing you some of those same currents I just showed you, but we're going to sort of simplify this a little bit. So we are talking about surface currents, and those are wind-driven movement of water at or near the ocean surface, as opposed to thermohaline, which was all the way, top to bottom in the ocean. And importantly, just like thermohaline, these currents are responsible for transferring heat around the planet, right? Stabilizing our climate, making things, nice. All right. As an example, I'll take this and I'll sort of superimpose these colors here. And this is a satellite photo of the Earth and the sea surface temperature. So red here in the middle in the tropics is warmer, and as you move to the poles here, top and bottom, the water gets a bit colder. And what I want you to do is I want you to kind of focus on this area. So here's us sort of here in Rhode Island. All right, and I'm going to zoom in here a little bit. And so again, here's us, and if you look right straight across the Atlantic, follow that red line, you'll see Spain. Well, what I want you to notice is that all this red, right, all this warm water, you go just where we are and above, it starts getting very blue. It starts getting very cold quickly. But let's move across the Atlantic, and let's look even further north. There's England and Ireland and even Scandinavia, and some of that warmth has made it up there. So it's made it actually quite habitable. In fact, there's a set of islands off the southern coast of England that if you go look at photos, it looks like something out of the tropics. And that's because these surface currents bring this tropical warmth north. It actually makes all of northern Europe habitable and, again, nice. All right, so the way we're going to break this down, again, looking at this, you'll notice some of these are labeled. And there's 5 major labels here. You have the North Pacific, South Pacific, North Atlantic, South Atlantic, and Indian Ocean. And over here is just, it's cut off. The Earth is round. More in the North Pacific. And these are called ocean gyres, all right? And an ocean gyre is the movement of water around the periphery of a basin. All that means is the water moves in a circle in each ocean basin. There's 5 major ones across the planet. So again, that thermohaline moved water all around the planet in this continuous conveyor belt, whereas surface currents are a little more specialized, a little more localized. And what they do, just like we kind of showed you the nice weather, is they take that warm water and they move it poleward. And then they take that cold water and they move it back to the equator. And again, in each of these 5 major ocean basins is this movement of water in this continuous kind of circular cycle. And they are not just one big current, all right? So take a look at this. Again, you can see the little blue lines here, but to dig in a little bit more, these gyres are made up of a bunch of different currents put together. So as an example, right here, we talked about Northern Europe and England being nice. Well, you may have heard of the Gulf Stream, and the Gulf Stream is one of these currents that blends into the North Atlantic gyre, and it brings that warm tropical water and air northward. And because these blend together, each one of their currents, right, you can sort of see here, they all have special properties. So you look at the thickness of these lines, and the thicker the line, the more mass is transported, and the higher the numbers too. Because we already said that a current is a transport of mass. So it's not the same everywhere, and we'll sort of break this down. So the first one we're going to look at are our western boundary currents, okay? And first I want to point out that when I'm talking east and west, because this is oceanography, you got to kind of think of being here in the ocean. So I'll show you this in a minute, but don't think about it on land. So the western part of this ocean basin is the east coast of the United States. You'll see what I mean here in a minute. So if I look at western boundary currents, right, those gyres we talked about, each one is on the west side of one of these basins. So again, east coast of the United States is our western boundary, and again, east coast of Africa, Asia, and Australia. And what these do, the reason they're special, is they are, if you guys saw in that last figure, or you're looking at your notes or slides as you should be along, there's that thicker line, okay? It's more mass transport. And you can think of these like fast-moving rivers in the ocean. So these are relatively narrow, deep, and fast-moving, and that's a western boundary current. The other one is eastern boundary currents, again on the west coast of the United States, but the east side of that ocean basin. And just like in here in the North Atlantic, these are still, you can think of them as rivers, but more like a lazy river. Like if you've ever been inner tubing and just kind of floating down a river, these are a lot more diffuse. They're wider, not as detailed boundaries. They're not as deep. So same amount of mass, but they just move a little slower, and they kind of bring that water back down to the poles. Now, to connect these two, eastern and western boundary currents, you have what's called transverse currents. Now, I'm not going to throw a circle around every single one of these because there's a lot of them, but you just realize that they're connecting here, 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 and so on and so forth. There's nothing particularly special about these currents other than that they connect the other two. So what I want you to really remember is that the western boundary currents are those deep, fast-moving, narrow movements of water, and then the eastern boundary currents are more diffuse. And kind of building up into our next lecture, we'll see the mechanisms behind that a little bit more. All right, so we've done that. Now the next thing we want to talk about is where these currents occur. So again, they are surface currents. So what that means, if you remember from our thermohaline discussion, we talked about the different layers of the ocean. You have the surface layer, the picnic line, and the deep ocean, and thermohaline works in all of those. Well, surface currents are really just in that surface layer, and it's about 10% of the ocean that these work in. And they are wind-driven, okay? So they're, as opposed to density gradients, which drive thermohaline, they are wind-driven. So wind-driven, how are they wind-driven? Where does this wind come from? Well, looking back at this picture, you can see that we have nice warm water temperatures here in the tropics and cold at the poles. And just like water currents and density, right, as the temperature goes up, density goes down and vice versa. And we know that less dense things will rise and more dense things will fall. So you can also think of it like this. You picture a radiator in your room, right? And that air heats up and moves up. And then maybe there's another part in your room where either you have an open window or maybe not a very well insulated window, and the air is going to cool and it's going to sink. So you put these two together, and overall, you're going to get this. You're going to get this movement of air, right, in a cycle. This is convection, right? Just this constant moving of air. And that's effectively what you have on the Earth's surface. It, basically, right here in the tropics is your radiator, and then where it's cold is your open window. And that air is going to move around. And it might look something like this, but this is a little simplified. So you can see the air rising at the equator and falling at the poles. But for a couple reasons, it's a little bit different. The first reason is the Earth isn't stationary, right? It rotates. Also, the Earth is round. So these two things are going to affect these a little bit. So rotation's one thing, and again, we'll come back to that. But let's talk about the fact that the Earth is round. Well, it's at least as round as $5 on Amazon are going to get you, but this will serve our purposes just fine. So what happens, because the Earth is round, let's say we have a sun, right? Massive sun. There we go. And it is shooting sunbeams at the Earth. Well, what you're going to see is right here at the equator, we get a very narrow, very high-intensity sunbeam. But then as you move to the poles, it starts to spread out. So the same amount of energy spread out over a greater area is going to reduce the amount of energy per area, obviously. And that's going to lead to overall lower temperatures. So it's not necessarily the amount of sunlight. Again, in the poles, you'll end up with 4 months of unending sunlight. But that doesn't do it. It's so diffuse that it's not going to heat up. All right. So that is the two reasons why you're going to end up with this. All right. You're still going to have warm air rising, cool air falling, but they're going to happen in cells, in these atmospheric air circulation cells all around the planet. The names of them, you can go look them up. It's not too important where they fall, but these are pretty stable cells all the time on the planet. And it's because of Earth's rotation and the uneven solar heating. All right, so where does that leave us? We now know surface currents, okay? Just like thermohaline, also responsible for regulating the Earth's climate, moving heat from the tropics to the polar regions. We know they're wind-driven. We know they work in gyres, right? These big gyres around the ocean basin. But maybe you still have some questions. Maybe I didn't answer everything. So I'll tell you what, we're going to do this. We're going to have a class participation assignment, and I'm going to ask you 3 questions that hopefully I'll be able to answer later. And the first one is, well, okay, we saw that these gyres go around an ocean basin. Why? Why do they travel in a circle? If they're pushed by wind and wind moves across the surface of the planet, why do they make this very stable circular motion in each one of these ocean basins? The second one is, well, why does wind travel across the planet in the first place? So we know that less dense air will rise and more dense air will sink. But why does it move side to side? Why don't you just stand there and have this uprush of air all the time? Okay? So that's your second question. Why does air move across the planet? And then finally, what is air? What is wind? What is air? I just want you guys to tell me, what do you think? Maybe you know, maybe this is simple. Maybe you just never thought about it. You're outside, it's windy, great, wind. Well, what is that? And I'll leave you with one weird thing before we get some even weirder stuff about this, is this picture here. So wind-driven currents, right? Well, take the surface of the ocean, and as the wind is blowing across in one direction, the mass transport, again, a current is transport of mass, actually moves at a 90-degree angle to the wind. And that's all I'm going to say about that for now. So go ahead, do your readings, take a look at your homeworks, email me with questions, come to office hours. Answer those questions. I think I'll make them due, Tuesday evening so that I can get you your next video. That should be fine. They're pretty quick. Again, you don't have to look this stuff up. I just want to know what you think. So do that. Think about it, and I'll see you guys next time.